Okay, let's start. Welcome to the DDPS seminar, everyone. Before we introduce our invited speakers, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. So please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Ricardo Vinuesa, who is an associate professor at the Department of Engineering Mechanics at KTH, Royal Institute of Technology in Stockholm. He is also a researcher at the KTH Climate Action Center and vice director of the KTH digitalization platform. He studied mechanical engineering at the Polytech University of Valencia at Spain, and he received his PhD in mechanical and aerospace engineering from the Illinois Institute of Technology in Chicago. His research combines numerical simulations and data-driven methods to understand and model complex wall-bounded turbulence flows, such as the boundary layers, and developing around winds and urban environments. Dr. Vinuesa has received, among others, an ERC Consolidator Grant and the Goran Gustafsson Award for Young Researchers. Today, Ricardo will talk about modeling and controlling turbulent flows through deep learning, which will be very interesting. So please enjoy a wonderful talk. Now, without further ado, let me pass the baton to Ricardo by asking one random question as usual. Today's random question is, what is your favorite things to do other than research?
Traveling.
Family, yeah. How many kids do you have?
Sorry, I meant traveling, but family.
You said traveling.
But family is a good answer too.
Okay. Sorry to misunderstood you.
No problem. No problem.
Yeah, you are doing the traveling right now, actually.
Yeah, exactly. I'm spending some days, some weeks now in the US actually. So it's very nice.
Okay. Okay, the stage is yours.
Yeah, thank you very much for the kind invitation. It's also an honor for me to be presenting in this prestigious seminar series. And as mentioned in the introduction, I'm going to be talking about turbulence and deep learning. My research is funded mainly by the ERC Consolidator Grant, the European Research Council, but there are other sources like CERC, which is the Swedish E-Science Research Council for e-science technologies. So I'm going to start by talking a little bit about success stories of machine learning. This technology is showing a lot of potential in a wide range of areas, including predicting text, economics, or image classification, as we can see in this slide. One of the first examples of data-driven methods being able to tackle complex tasks was when in 1997, the IBM Deep Blue machine defeated Garry Kasparov, who was the world champion of chess at the time. He didn't take the defeat so well, actually. And it turns out that playing chess is actually quite easy for a machine, because essentially through brute force computing, one can get quite good performance, and one can define the complexity of a game. And games are very widely used in machine learning because they define narrow but challenging tasks. One can define it by taking the number of moves that you can do in a typical turn, and raise it to the power of the number of turns that a typical game has. So as we can see here, the numbers of chess are much lower than those of the game of Go, which has become now very popular thanks to Google and DeepMind. So this metric of m to the power of t is many orders of magnitude larger, in the case of Go. And this game, Go, actually requires some sort of intuition, some sort of strategic thinking to be able to be played. I mean, it's not enough with just brute force computing and analyzing all the possibilities. One needs to be able to really try to predict and foresee in the future what the developments are going to be. And trying to leverage the potential of machine learning, the team of DeepMind, Silver and others in 2016, they published in Nature their work developing the Alphago algorithm. So in this algorithm, they showed the games of the best human players of Go, and they could actually defeat the world champion Lee Sedol, as you can see here, by 4-1 using this algorithm. That was a very very astounding accomplishment, because it was expected that machine learning would be able to play Go in quite some decades ahead, but actually it was achieved now 6 years ago. So that was quite some remarkable results there. And maybe even more interesting is the next evolution of this algorithm, which was the Alphago 0. And in Alphago 0, the algorithm is not given any knowledge, any human knowledge. It's just given the rules of the game. And then the algorithm, by playing against itself using reinforcement learning, is able to, as you can see here, this is the performance as a function of the training time. In less than 2 days of training, it was able to reach superhuman performance. So actually, there was quite some interesting potential of this technology for this narrow task without using any human input, just using the strategies that were developed through self-learning in this playing against itself in this reinforcement learning context. So there is quite some interesting areas where machine learning can actually be applied. We have a recent article in Nature Communications where we looked at how AI, more generally AI, can affect the sustainable development goals of the United Nations. It turns out that 79% of these goals can be positively affected by AI, whereas 35% can be negatively affected by AI. One should be aware of the fact that even if the result is mostly positive, there are many negative areas that one should be aware of when deploying these technologies, and the environment and the society appear to have the largest positive potential of this technology. Now, we were talking about interpretability before. Of course, many of these models, of these deep learning models, are actually, acting as black boxes, right? So it's really not possible to establish a clear connection between the inputs and the predictions that are being obtained from those inputs. And we argue in Nature Machine Intelligence that for any applications with some real impact on society, on sustainability, on engineering applications, one needs to develop interpretable methods. And there is some interesting work from Kramer and others from Princeton where they added layers of interpretability on the already trained deep learning methods. And we argue in our paper that that can also be achieved as well, basically by symbolic regression, so that one can actually make predictions that can, in fact, generalize sometimes even more than the original deep learning model. This is a quite up-and-coming area of research, and of course, this is very, very relevant for a very wide range of applications. My main topic today is going to be fluid mechanics. And machine learning has helped fluid mechanics in a wide range of areas. Perhaps a very seminal work 20 years ago by Milano and Komosakos, where they could use neural networks to predict the near-world region of a channel. That was a quite interesting seminal approach to these data-driven methods. More recently, there have been studies looking at subgrid scale modeling for large area simulations, RANS modeling as well. There has been quite some potential to generate synthetic inflow and boundary conditions that can help to produce more efficient CFDs, CFD, which stands for computational fluid dynamics, so CFD simulations. And also, there is quite some interesting applications to flow control to be able to reduce the drag or enhance the mixing, and to use pins, physics for neural networks, in the context of sensing as well. So there are some interesting directions and some interesting areas where machine learning is already helping and can help even more for fluid mechanics. In fact, we have just published in Nature Computational Science a review article together with Steve Branton, where we highlight the potential of machine learning for CFD, for computational fluid mechanics. And what we find is that there is quite some potential to accelerate direct numerical simulations, to improve the modeling, both in the context of LES and RANs, and to improve the robustness and generality of reduced order models. And I will be talking about that also later in this presentation. So both in terms of modeling and acceleration of the simulations, there is quite some potential also for machine learning, and you can also read more about our perspectives on this review article that you can find here in this reference. Okay. So today, what I'm going to do is that I'm going to focus on several examples where we have used machine learning to either help the modeling of turbulent flows or enhance possibilities for controlling those turbulent flows. And the first example is what we call non-intrusive sensing. So in non-intrusive sensing, what we do is that we want to measure at the wall so that we can predict what happens above the wall in the flow without having to stick sensors in the flow itself. Because of course, when we start to put the probes, we're disrupting the flow, we're creating other effects, and it's quite efficient to actually measure just at the wall and perform that prediction dynamically at each time step. So what we use is three quantities that we measure at the wall pressure and the two wall shear stress components. And we use computer vision techniques, CNNs, but also other tools to predict what happens to the three velocity fluctuations at different wall normal locations above the wall. So above the wall, we can actually predict. And one motivation for this non-intrusive sensing approach is flow control. Because if we know what is happening on the flow at each instant, we can design better controllers to be able to reduce drag or do any other application that we may want to do with the flow. By the way, these results are presented in the Journal of Fluid Mechanics, so you can see the reference here by Guastoni and others published last year in 2021. Okay. So the first thing that we do is that we create a database of direct numerical simulations, DNS data, using a Fourier-Chebyshev code, and we consider a turbulent open channel. So we have one wall and a symmetric condition at the top. That's just to simplify slightly the dynamics of the large scales. We consider two Reynolds numbers, friction Reynolds numbers of 180 and 550. These are the domain sizes, which are large enough. And we use this DNS data, this highly resolved numerical data of the flow, to be able to train deep learning models to make the predictions that I was mentioning. No? So from the wall to above the wall at different locations. And what happens is that turbulence exhibits coherent structures, right? So turbulence has certain patterns. And if we look at the wall, those are going to be 2D images. So of course, using fully connected networks they're not going to be very efficient in this sort of prediction. And we go to computer vision. So we start with CNNs, convolutional neural networks, to be able to exploit the spatial correlations of the data, which correspond to the coherent structures present in the flow, to be able to leverage those and improve our predictions. No? So in CNNs, and I guess most of the audience here is very familiar with them, we essentially have a kernel, a 2D kernel, which can have a certain depth as well, which is sweeping through the input image. And then we obtain a feature map based on these convolution operations that are being applied. And in this case, since the kernel has size 3 × 3, its value of the output, which is a feature map, each of these grid points receives information from 9 grid points of the input. And that depends on the kernel size and how we are designing the convolutions. So essentially, one of the architectures that we consider is this one, where we have, this is a CNN, a convolutional neural network. We have 3 inputs here, which correspond to the 2 wall shear stress components and the wall pressure. We have 3 outputs here. Those are the 3 velocity fluctuations at a certain wall normal location. And we have a total of 6 hidden layers with a number of filters that you can see on each of the layers. So of course, each of those filters is associated with a feature map that is identifying one or more features of the input. And we can actually see that, of course, we have a reduced number of parameters in the first layers, no, because of the convolutional aspect of this architecture. And the idea is the following: because we have structures in turbulence, and we want to be able to exploit those spatial correlations to make predictions. In the first layers, we're going to identify very abstract and simple features on the input data. So those could be edges, lines, circles, things that are quite simple. And of course, because of the concatenated application of convolutions, when we get closer to the output, we will build progressively more complex structures. No? We'll build more elements that are more realistic and more aligned with what you have in a turbulent flow. And that's very interesting, right? Because what happens is that through this concatenated application of convolutions, we can hierarchically build more and more complicated features which correspond to the turbulent structures. And turbulence works like that. Turbulence is also very hierarchical. You have smaller scales that interact, and one can actually produce turbulent kinetic energy and create larger scales in a quite hierarchical manner. So the way that these structures are being produced is very nicely aligned with the way in which CNNs learn. So there's a quite nice fit there to predict turbulent structures. One additional note is that we have now been working on even deeper networks. So if you maintain the number of parameters constant, which means that we reduce the number of filters per layer but increase the number of layers, you can actually get even better predictions. No? And that goes in the direction of this concatenated application of convolutions that help us to really build very good and realistic coherent structures. Okay. So this is how the CNN looks like. And again, this is the reference in JFM. So these are the three wall quantities that we are using as input. And these are the three velocity fluctuations that we're trying to predict. Okay. Everything that I've shown you so far is what we call the Fcn method, the fully convolutional network, which relies on taking information at the wall, which if you look at the wall is just going to be a 2D plane, and predicting directly the information above the wall, which is going to be another 2D plane. But something that one can do instead is, rather than predicting directly the full plane, is to do POD, proper orthogonal decomposition, or principal component analysis, depending on which is your community. So one can do POD on these subdomains. Therefore, what we do is that we separate the spatiotemporal problem into spatial modes and temporal coefficients, and then we only need to predict the temporal coefficients of those modes, right? So this is in principle an alternative approach that can help us in certain cases, and this is documented in these two references, and this will be denoted as the Fcmpod method. So we will have the Fcn and the Fcmpod. So I'm going to show you predictions at RE-tau 550. This is the higher Reynolds number that we consider, and these are instantaneous velocity fields of the stringwise velocity fluctuations. Okay, the first column is y plus 15, which means that this is the region of the near wall peak, and the second column is y plus 100, which is already in the outer region. The reference is the third row. That's the one labeled as DNNs. So we want to target these two flow fields that you see here. The first row is based on the extended POD. So the extended POD is a method that is formally equivalent to linear stochastic estimation. So essentially it's a linear prediction between the input and the output. And what we can see in this comparison is that the linear method is able to predict some things, but the problem is that the streaks are significantly attenuated, and many of the nonlinear interactions due to modulation are not very well reproduced by this method. No? So in a way, the linear prediction framework will capture the superposition mechanisms of the large scales, but not really so much the modulation, which is a nonlinear phenomenon. If we go to the nonlinear methods, which are the CNN-based approaches, what we see by comparing the second and the fourth row is that the Fcn approach basically nails the flow at y plus 15. We can get excellent predictions of the streaks, of the near wall peak and the near wall fluctuations. We get excellent results there. Of course, as we move farther away from the wall, the signals are less correlated, so it's more difficult to get good predictions. But at y plus 100, the Fcmpod gets better results. And of course, there is a certain filtering effect. We don't have a perfect prediction of the flow at y plus 100, but the Fcmpod can identify where the streaks are, their sizes, and their locations. More interestingly, we can argue, because the Fcmpod works better than the Fcn, that close to the wall, you should use the Fcn. You predict directly the whole signal. Far away from the wall, it's better to do POD first, and then only predict the temporal dynamics of those spatial modes, because you can basically encapsulate the information more efficiently in few POD modes when you have these very large scales for which we only need to predict basically the temporal dynamics. Okay. So this is about the instantaneous predictions, but we can also look at the statistical features of the flow. So what we show here are the stringwise, wall normal, and spanwise velocity fluctuations. The black line are the DNS results. and the horizontal axis is the wall normal location in inner units. The triangle is the Fcn prediction. The blue dots are the Fcmpod, and the square is the extended POD, is the linear method. So what we can see by comparing with the reference is that, of course, all the predictions get worse as y plus increases. That's expected. The near wall peak is very well predicted with Fcn. So we get less than 1% error of the near wall peak, which is quite remarkable. And the other interesting thing is that at y plus 100, the blue dot is above the triangle. So that's where the Fcmpod takes over and becomes a bit better than the Fcn. And in all of these cases, the linear method is worse than the CNN-based methods. No, I mean, as expected as well, because we can only reproduce the linear scale interaction mechanisms of turbulence, but not the nonlinear ones, which are quite well captured through the CNN approaches. Okay. By the way, the error that we make at y plus 100 with the Fcmpod is 26%, which is acceptable if you want to do flow control, because then you can actually see at least where the large scales are. Okay. So something that we also did was transfer learning. So in transfer learning, as many of you know, we basically try to reuse what we learn in one task for another one that is not too different, but not too similar either. In this case, what we are doing at Arita 180 is to take a network trained for predictions at y plus 15, so close to the wall, and try to see if the predictions at y plus 50, which is a bit farther away from the wall, can be benefiting from transfer learning. To do that, what we do is that we freeze the three first layers. So as I mentioned before, these ones are going to be identifying smaller things and more abstract features. And we can expect that at the two locations, the small scales are going to be similar, and it's going to be the larger scales that are going to be a bit more different. That's why we will retrain the information of the layers closer to the output. Okay. And you can see all these results in the Journal of Physics conference series, also by Guastoni and others. What we do is that through transfer learning, we can get the same level of accuracy as with the original network, but reducing the amount of training time by a factor of more than 4. So we can actually train these networks for turbulence predictions in a more efficient way. We also did this in the context of Reynolds number effects. So we took the network that we used to make predictions at Arita 180, and the training at Arita 550 was initialized from the weights of 180, right? So we transferred the weights, and instead of having random initialization, we just started with the weights of 180. What we can see is that we can reduce the amount of training data again by a factor of 4. So we can actually obtain the same level of accuracy, but reducing much more the amount of data, which in this case, the simulation at 550 is much more expensive than the one at 180. So if one can do most of the training with a very cheap simulation that basically you can run in your laptop, and then the requirements for high performance computing are significantly reduced, then we are doing something quite effective, no, for our training of our deep learning models. Now, what happens if instead of having the full signal at the wall, so if you take the wall information and you look at it, instead of having the DNS level of resolution, you only have few sparse measurements there, right? Which is what would happen in a wind tunnel experiment, in a real world realization of this. Well, what we did was to employ generative adversarial networks, GANs, which again, many of the people in this audience are familiar with. This is a schematic representation of the GANs, in which we have two parts. We have the generator and the discriminator. So the generator, what it's doing is it's producing high resolution images based on low resolution images that need to basically follow the statistical distributions of the reference data set. And the discriminator needs to differentiate which of the high resolution images were from the original data set and which ones were produced by the generator, right? And because these two networks, or these two parts of the network, have antagonic tasks, they can be trained together using game theory. And essentially, we can get a generator that is very good at producing realistic images. And that's what we leverage here in this architecture, which has two steps. In the first step, we go from the low resolution data at the wall to high resolution data at the wall. And in the second step, we use that high resolution data to produce the predictions of the flow above the wall, right? So we go from coarse data to fine data and then to prediction. All these results are presented in Physics of Fluids. So you can see this article from last year. This is the instantaneous streamwise wall shear stress component. This is the DNS, so this is the reference. And at the top, I am downsampling by a factor of 4, 8, and 16 square. So you can see that the 16 squared case, this one is actually quite coarse. And this is similar to what you could get in an experiment, just few measurements at the wall, right? And what you see on the second row are the predictions. And we can actually get quite good predictions, even in the, for the low downsampling, we get very good predictions. For the high downsampling, even if there is an attenuation of the streaks, we can actually see that the streaks are in the right location, they have the right size and the right spacing in the spanwise direction. So we can actually use this for flow control quite effectively because we are getting some insight into the characteristics of these streaks. And if we do now the predictions above the wall, what we get here in the first row is the DNS, right? The first column is y plus 15, then 30, 50, and 100. So we're going progressively farther away from the wall. And then the next rows are the different downsampling levels, no? 4, 8, and 16. So obviously the easiest prediction is this one, right? Because this is very close to the input and there is a low downsampling. And you can see that the prediction is excellent. It's really, really good. The hardest prediction is this one, because we are very far away and we have quite a lot of downsampling. Even in this case, what we can see is that the streaks are very well located. So even if I want to target large-scale control, we can actually get very effective control approaches to be able to target these structures. So even for an experimental realization of this flow control or this non-intrusive sensing plus flow control strategy, we can actually get very, very good results that can help us in the context of the closed loop control. Okay. So everything that I discussed so far was based on predictions from the wall to above the wall for non-intrusive sensing. But one can think of the opposite problem. What happens if I want to use information from far away from the wall to predict the flow closer to the wall? And this is an important problem when one is thinking about off-wall boundary conditions, where one wants to replace the whole near wall region by a boundary condition where you can develop good wall models. And we try to use this via CNNs, right? This work, you can find it in arXiv, and this was presented at ETMM last year, so you can find the arXiv preprint in there. And essentially what we see, we try to reproduce some of the work that was done by Mizuno and Jimenez. So what they did is that they took the overlap region of a channel and basically rescaled the input and set it at the location close to the wall to develop a wall model. We tried to do something like that using CNNs. And we consider the case at Aritau 550. We are having in the three columns the U, V, and W fluctuations. The input is at y plus 100. So these are the three input quantities. The output, so the prediction, which is closer to the wall at y plus 50, is the second row. So we're trying to predict these quantities over here. And the predictions are the third row that you can see here. So we can actually see that visually, the instantaneous flow is in quite good agreement, and we can reproduce, if we compare the second and the third rows, we can reproduce most of the features of the original data quite well. But this prediction is inherently more complex than the previous one for two reasons. When you're using the outer flow to predict the flow closer to the wall, you miss the effect of the small scales that is imprinted at the wall. So that's already missing when you're trying to make those predictions. And second, when we are trying to use a CNN to predict from the large scales as input, the receptive field is going to be a small part of those large scales, which also complicates extracting the relevant information from those scales to make my predictions. If we look at the results, here we have the power spectral density. This is the two-dimensional spectrum in the stringwise and spanwise direction at y plus 50. The shaded contours are the reference and the orange lines are the prediction. We can see that clearly we're missing some of the small scales which is not surprising. This is what we can expect from the lack of small-scale information at the input, and some of the energy is a bit displaced, no? But overall, the spectra looks physical. I mean, there's a bit of a discrepancy, but still, it's not that bad. And we have around 20% error in the predictions, no? Which for flow control, it would be good. For imposing it as a wall model is a bit high, so one should also, well, try to explore other alternatives. But in principle, we could solve the problem of the missing scales with a GANs-based approach, probably. And we can also work with pooling, max pooling, for example, to be able to solve the problem of the receptive field and the large scales. So there are some possible strategies that one could try to benefit from in the context of these predictions. Another problem that I'm going to mention briefly, and if you're interested in it, we can also discuss it more later, is the use of physics-informed neural networks, PINs, for RAN simulations. And RAN simulations are the simulations based on Reynolds averaging, where we are actually trying to model the contribution of the Reynolds stresses to the mean flow. This work has been published recently in Physics of Fluids, so you can see the reference here. And what we see is that with PINs, we can take the 2D RANS equations for incompressible flow and use the PINs framework to solve these equations without any model for the Reynolds stresses. So the Reynolds stresses are variables that are being solved as part of the algorithm that we are trying. Okay, and let's keep in mind that PINs is basically trying to minimize the residual of the RANS equations. So it's trying to solve the covariant equations in a similar way to what you would do with a spectral element method or a finite difference method. The only advantage of PINs is that you can get away with coarser resolutions, because with automatic differentiation, you don't need to really resolve the gradients so much. You still need to resolve some things and propagate the information to the boundaries, but you don't need to resolve the gradients so much. And in certain niche applications, like in RANs, for example, one can actually get at a similar computational cost than that of the industrial RAN simulations. Basically, we can get a performance that is much better than that of the typical RANs models, basically. So this is a periodic hill. This is a typical example of flow with separation. There is a quite big challenge, no, for models, and we're comparing with DNNs, and we can see that we get a very good representation of the separation bubble, the reattachment, and the streamlines. So we get around 2-3% error in the mean, a bit higher error in the Reynolds stresses, but you can actually see that we get a very good representation of the DNS data in this flow configuration. Okay, so PINs can actually help us. And of course, there is some limitations as well, but in certain niche applications, we can actually get interesting results from PINs. Okay. Now, another example that I like quite a bit is that of using reduced order models and utilizing the advantages of autoencoders to build nonlinear reduced order models, no, in turbulent flows. So we can actually try to obtain nonlinear reduced order models by reconstructing the nice properties of POD, which are the optimality and the orthogonality of these representations. Okay, and through the orthogonality, we're going to try to have interpretable nonlinear modes. This work was published also this year in Expert Systems with Applications. So this is the reference, and I'm going to be describing a little bit, first of all, the data set. So there has been some work of autoencoders on 2D cylinders, but this is one of the first applications to a turbulent flow, a complex turbulent flow. This is a well-resolved large eddy simulation, very detailed flow in a simplified urban environment. So the flow between two buildings, you can see the level of detail that we can obtain, and you can see Latpita and others for more details. And we have a total of 1,200 instantaneous flow visualization, flow realizations to be able to train our reduced order models. So we consider different autoencoder-based architectures. And the first one is the classical CNN autoencoder. As mentioned before, turbulence has a certain spatial information and spatial correlations that can be exploited through CNNs. That's why we employ the CNN autoencoder. As many of you know, an autoencoder is a deep learning architecture in which you're trying to reproduce the original data, reconstruct the original data, but you're applying progressively dimension reductions until you find a very compact representation of the original data in the latent space, right? Which is the bottleneck of the autoencoder. So this is the CNN-based autoencoder, quite standard. The second one is the hierarchical autoencoder. And this one is aimed at obtaining the optimality property of POD. We want to obtain modes that are ranked based on their contribution to the reconstruction. And this was proposed by Fukami and others. The way that this works is that you have first an autoencoder configuration where the latent space has size 1, and that allows us to obtain the first latent variable, the first latent vector. Fixing that latent vector, we have another autoencoder of size 2, where we want to train and obtain a new latent variable, R2, which is able to reconstruct the original signal by fixing R1. And we can do that recursively. In the third autoencoder, we fix modes 1 and 2, and we want to fix the third one by fixing the dimension of the latent space to 3, so that we can obtain a sequence of modes that have progressively less and less contribution towards the reconstruction. Okay? None of the autoencoder configurations that I mentioned so far gives you orthogonal modes, and that's a desirable property if you are building a reduced order model, because you want the modes to be able to be interpretable. Okay? To be able to embed the orthogonality, we consider beta variational autoencoders, which are ways in which we can introduce stochasticity in our model. So we consider that P of X is the distribution of the original data, P of R is the distribution of the data in the latent space, okay? And the goal of the beta VAE is to maximize this quantity, where P theta of X is the marginal likelihood. So it's basically an approximation of the original data given the parameters theta of the network. So in the variational autoencoders framework, this quantity over here, which basically wants to give me the marginal likelihood of the original data given that that we have the latent space variables, this is what we call the decoder, because it will obtain or it will recover the original data. And this is, of course, a generative model. So we're sampling from the latent space distribution to obtain that generative model of the original data. And conversely, this distribution over here of R, which is the latent variables given the original variables, this is an encoder, right? Which will be the recognition model that takes us from the original space into the latent space, and the decoder will take us from the latent space to the original, to the reconstruction that we want to have, okay? So this would be the setup for a beta variational autoencoder. The interesting thing and the way in which we can introduce stochasticity is that in the encoder, we assume a Gaussian distribution like this one, okay? And we can sample from this marginal likelihood, from this distribution, through an auxiliary normal distribution of noise. So we have the latent variables are given here, mu is the mean, sigma the standard deviation, and this noise follows a normal distribution. So the loss of the beta VAE is given by this quantity over here, where we are introducing a penalization factor beta, that's where the name comes from, which promotes two different things. First of all, we want to promote learning statistically independent latent variables, which basically minimize the distance between PR and the product of its marginals. And on the second hand, on the second side, we want to minimize the size of the latent space, so we can learn a parsimonious and disentangled representation of the data in the latent space. That's what the beta VAE is doing. And of course, this is a hyperparameter. I will tell you more about its effect. This is how the model looks like. So the decoder is the generative model, where I can recover the original data by sampling from the latent space, and the encoder is the one where I am obtaining the variables in the latent space. Okay. So these are some results. This is a reference instantaneous field that you can see here. This is the flow between the two obstacles. If I take 5 POD modes, I only reconstruct 32% of the energy, whereas with the autoencoder approaches, I am always around 90% of the energy. In fact, the beta VAE is 87% of the energy with orthogonal modes, and I will show you more about the orthogonality. Here you can appreciate the level of detail that we can obtain with reconstruction, which basically tells me that with this autoencoder-based model reduction, I can obtain very compact reduced order models. With 5 autoencoder modes, I can reconstruct a significant fraction of the energy, whereas for POD, I would require hundreds of modes, which in principle tells me a little bit of the potential of these autoencoders for turbulent flow simulations and turbulent flow modeling. This is the determinant of the correlation matrix among the 5 first modes. As you can see, of course, the POD has 100% orthogonality. The beta variational autoencoder has more than 99% orthogonality, which means that a certain physical phenomenon will be mapped to a particular mode and not a number of modes. And the orthogonality of the other 2 autoencoder approaches is actually quite low, right? So in principle, if we want to promote interpretable modes, the beta variational autoencoder approach is actually quite convenient. There is an interesting effect of the beta parameter. So of course, here I'm plotting the parameter beta, and I'm representing you the orthogonality, which increases with the parameter beta, and the percentage of reconstructed energy, which decreases with beta, obviously, right? Also, the number of non-zero variables is decreased when I am increasing the parameter beta. So of course, the penalization, if I have a higher penalization, I will have a more parsimonious model, I will have fewer variables in the latent space, and I will also have more orthogonal values, but I will have a worse reconstruction, right, through that penalization that I'm introducing. So you can see how the latent variables are actually changing when I'm reducing the value of beta. I have a total of 10 non-zero variables with the smallest value of beta, and only 3 non-zero variables in the latent space with the highest value of beta. So one can actually choose in terms of performance and in terms of physical properties the type of hyperparameter that we want for this particular penalization. Okay. And for the beta variational autoencoders, what we also did was to develop an algorithm for the optimality. So we basically are able to recursively classify the modes in terms of their contribution towards the reconstruction of the signal, so we can actually rank them from more to less contribution, meaning that we have an optimal reduced order model and an orthogonal one, right? So in the case of the beta variational autoencoder, those modes are very orthogonal. And why is that important for interpretability? I'll give you an example. I'm showing you the first 5 modes for the case of the 2D obstacles, right, that I have from the beta variational autoencoder, the POD, and the other 2 autoencoder approaches. And of course, the POD exhibits clearly large-scale shedding. That's quite clear from the data. POD is very good at identifying these things. The CNN autoencoder and the hierarchical one, they don't show you any physical phenomenon that one can easily identify. They show a lot of high-frequency components that are associated with the turbulence fluctuations, whereas the beta variational autoencoder gives you the large-scale shedding as well. So we can actually obtain nonlinear and interpretable modes in the case of the beta variational autoencoder, which is actually quite an interesting result if we want to try to learn some physics from this. So in a way, the variational autoencoder is giving us a more compact representation. We need fewer modes than POD. Through adding higher frequency content in the nonlinearities that are present in these modes, but retaining the interpretability. So that's a quite nice property for this strategy towards obtaining these reduced order models. Okay, so this is when it comes to the variational autoencoders. And the last example comes from deep reinforcement learning for flow control. So and this was presented by Guastoni and others in the APS last year. Essentially, when we have a reinforcement learning framework, I have an agent, which would be the neural network, which is interacting with an environment, which would be the flow simulation that we are trying to develop. Well, given the state of the flow, we decide some actions to be applied to the environment, and we obtain a certain reward that we want to maximize. No? So the goal of the reinforcement learning is to develop a policy pi such that given the state of the system, I can actually decide what are the best actions, no? to be able to maximize the reward, which in our case it will be to obtain the minimal drag in the channel. Okay. And in this case, we consider an easy example, a 2D channel, with us basically through suction and blowing, we induce a separation bubble at the lower plate, and through actuation upstream of that bubble, we want to reduce the length of that recirculation region. So we have a classical solution that is periodic, and we want to see whether the reinforcement learning is going to provide us a more nuanced, a more sophisticated control approach to this. No? And what we do is that we observe, so here is the flow field. In colors, you can see the negative velocity, so this is the bubble. The dots are the probes that we are actually using to sense the flow. The arrow will be the reward, so we want to minimize the arrow, the separation length. And this square over here is the place where we are setting up the actuation, which is modeled through a body force that wants to emulate blowing and suction. And we are trying to get the amplitude of this body force. Okay. So this is a little bit the setup for this 2D case. And what we can obtain here on the left, I'm showing you a video. So you're actually seeing how the control looks like. What we see is that we have two characteristic and dominant frequencies in this control, one associated to the spacing of these wave packets that are being sent, and another one that is associated with the characteristic time of the bubble itself, right? So it seems that we have at least two dominant frequencies in this DRL-based control strategy. And what we can see is that we can compare the reduction of the separation length with the DRL and the periodic forcing. In the periodic forcing, we have around 20% bubble reduction, whereas in the case of the DRL, we get around 30%. So we get better performance when we are actually having the DRL done with a classical solution, which is a single frequency and it's a bit more simple. And we are actually extending this DRL framework for flow control to perform opposition control in the context of turbulence. So we are doing this in turbulent channel flow to be able to minimize the drag and control turbulence. Okay, and this is a summary of what I have discussed today. So we have used DNNs for non-intrusive sensing, achieving very good predictions. We also developed off-wall boundary condition strategies. We applied pins for run simulations. We use nonlinear autoencoders for model reduction. And finally, I presented you some results that we have on deep reinforcement learning for flow control. I would like to thank you very much for your attention. You have my contact information here, my email, my lab, and my social media. So you can contact me if you want to discuss more. And I will be very happy now to answer all your questions. Thank you very much.
Thank you so much for the wonderful talk, Ricardo. That was really, really wonderful. I learned a lot. All right. So we do have a series of questions in Q&A. I'm not sure you have access to the chat room, but I can facilitate.
Let me see. I saw. Okay, I think I do have access.
Yeah. All right. Starting from the Pat's comment, he will always wants to emphasize symbolic regression is same as the equation discovery. Do you want to?
That's okay. I just wanted to point the speaker to another literature that's older than what he calls symbolic regression.
Symbolic regression, yeah. Symbolic regression is the recent.
It's the same thing. We used to call it equation discovery. Some of us still do. But let's but let's move on.
Yeah, let's move on. Okay, so
thank you very much for the reference. I will certainly look into it, and we can discuss more.
Sure. Well, there's a link there.
Yeah, I saw it. I saw it. Thank you so much.
All right, sounds good. Okay, next question is from the Jeremy. Slide 15. Yeah, so if you can go to slide 15. Are these averaged velocity profiles? Do you have an impression of what one-time profiles of velocity fluctuation profiles conditioned on a particular wall stress fluctuation look like?
Yeah, so These are the statistics, the turbulence statistics. No, so the RMS fluctuations. These are average in time and the homogeneous directions. The instantaneous flow can be found here. So these are instantaneous realizations of the flow at particular Wall-Normal locations. So because we do predictions of 2D planes, it's a bit more difficult to get the three-dimensional distribution with conditional averaging for the different events that could happen. But some recent work that we are currently conducting with my colleagues in Madrid, we are actually doing predictions of the 3D flow. So we're using GANs to do non-intrusive sensing of the 3D flow. And then these conditional representations of the flow on particular intense events can be viewed in more detail in those 3D cases. Since these are 2D, it's a bit more difficult to really get good representations of the events in that conditional average.
All right. Well, thank you. Next question is by Pat. I think, okay, so he asked, could you revisit what you are predicting? What are you
It's
comparing?
related to the previous question. I mean, RMS has always been a questionable metric, but at least I want to understand where it's coming from. What are you comparing?
Yeah, RMS, I mean, in the context of wall-bounded turbulence, this is a pretty standard physical quantity that one is.
I believe it's standard.
Mhm.
Wait, well, RMS, you mean root mean squared error, correct?
Root mean square fluctuations.
Oh, sorry. Hold on.
Yeah.
No wonder I'm confused. Okay, so it's not RMSE.
No.
Okay.
So I'm sorry because the audience, of course, is a bit heterogeneous. So this is a bit more on the fluid mechanics side. So the flow, the turbulent flow is fluctuating. What you can see here are the patterns of the fluctuations. And then one can take the RMS of those fluctuations, which are very important physical quantities in the context of turbulent flows.
What is RMS?
Sorry?
What is it again, RMS?
Rho means square fluctuations.
Fluctuations at spatially.
Yes. So the fluctuations are average in time and in the two homogeneous directions. So in the case of a channel, the stringwise and spanwise directions, and they are plotted as a function of the distance from the wall.
So this is some kind of measure of how much variance there is.
Yeah, exactly. The variance of the fluctuations. So what you can see here.
That helps. And so this is an aggregate measure, and you were trying to predict this aggregate measure. Is that correct?
Yeah, I'm predicting the magnitude of the fluctuations, the variance of the fluctuations at different distances from the wall. Exactly.
All right. Thank you.
Thank you for the question.
Okay, sounds good. Yeah, pins. Another question by Pat. Do you really need another OPEC acronym?
Not a question.
Not a question.
Just complain about acronyms.
That you need to talk to George Karnerakis, no, who developed the pins framework.
Well, you don't have, but I'm talking to you because you're using it. You didn't actually use it. You said it here. Physics informed neural networks. That was fine. It's just that then if you start putting that in papers, you're going to make them less accessible to people who don't know what's going on. And AI in general, maybe fluid dynamics too, but AI in general has been really overused applications like this for decades. I just wanted to discourage it. That's why I was making fun of you.
Well, it's unfortunately it's getting popular these days. So
I believe it. That's why we have to stamp it out now.
Well, at least I highlighted in my slide what it stands for, so you can have it. But I agree that there are too many acronyms. That's absolutely true.
All right, sounds good.
I mean, part of it is that I'm concerned that, especially about hiding it, people are going to say, well, physics informed neural networks as opposed to physics informed other approaches, because there are other approaches to doing physics informed model discovery.
Yeah, that's
neural
true.
nets.
Yeah, that's true. That's true. Yeah. So there's a subtle distinction that we have to be clear about.
And I agree. I mean, in particular, pins. I mean, from the name itself, you don't get the full picture of what it actually is, because I mean, it's more using the machinery of deep learning to solve PDEs. It's not so much embedding physics in the network. It's more just solving a PDE with the machinery of deep learning. So in even the name in this case, I mean, there is some things that one could actually argue about the name itself. So yeah, I mean, it's important to know exactly the methods that we are talking about and what they actually do.
Yeah, I mean the way you used the pins here is you put the residual of the PDE and then minimize it in the training.
There is actually two terms in the loss. I didn't get into too much detail, but one term is to minimize the residual of the PDE inside the domain, and the other term is to match the boundary conditions, because you need to be able to match the boundary conditions as well. And then that's the two terms of the loss that we have here.
Yeah, I remember I heard a talk a few months back in somewhere where someone pointed out there are very radically different ways to use physics knowledge in this context, right? One of them is as a regularization term, but there are other ways too. And you're using it to regularize things. Is that correct?
Yeah.
In this case, even it's just solving the PDE. We're just our loss function is based on the residual of the PDE. But of course, I mean, another way that we have tried is through embedding in the non-intrusive sensing. So in this, in these predictions that you see here, right? You can use some of the physical properties that you know about the flow, for example, incompressibility, to simplify your prediction. So that becomes a step additionally on the data-driven approach that you're using, which of course, yeah, I mean, embedding physics in these neural network models becomes a little bit, yeah, a little bit confusing with the nomenclature, because there are many different ways of doing it, and they get confused quite easily. Yes.
All right. Let's move on. The next question is by Jeremy. Let's see. For the channel flows, do you have an impression if wall shear stress or pressure is more predictive for velocity fluctuations? I think pressure measurements may be easier for an experimentalist.
Yeah, that's a very good question. So you're right. Pressure measurements are easier from an experimental point of view, although the wall shear stress measurements are becoming more and more feasible with enough spatial resolution. Turns out that to predict the U prime, the stringwise wall shear stress is the most important quantity, which makes sense, of course, because they both contain information of the streaks. To predict the V prime is the pressure, the one that is more important. So depending on what you want to predict, you may have to measure different things. And this is something that we have been also analyzing in the context of Shapley, the Shapley framework for explainability. So that's actually, so this Shapley framework gives us something very consistent with the physical intuition that one can actually get for these flow cases.
All right, next one is by Pat. How large are your training sets of CNNs, and how many runs do you need for the reinforced learning application?
So the CNN is for the non-intrusive sensing part, which is this first part. We are talking around 5,000 to 10,000 snapshots of training. That's what we need for these predictions. For the reinforcement learning, I mean, it's expensive. Here I have some results as a function of the time step in a particular episode, but we're talking hundreds of episodes, and that's for the. So these are the time steps of a particular episode. That's for the 2D case. For the turbulent channel case, it's even more that one needs. But we're using a framework where we have parallelized the exploration space, so we can have 16, 32 different processes running episodes in parallel and communicating, so that it can be done a bit more efficiently. But yeah, but the exploration, it's quite costly in these cases, yes.
Okay, sounds good. The next one is from Joita. He wants to connect with you later via
Yeah,
email.
absolutely. I mean, I guess my information, I mean, I can write my email in the chat, and I guess my information will be available. You see it also in the slides. So feel free to email me. I will be happy to provide you more information, to have a call and discuss more. Absolutely.
All right, sounds good. Okay, going back to the pins, my questions. You need the collocation points.
Yes. So
how many collocation points did you?
So this gives you an idea of this is an extra slide of the periodic hill. So that's a typical mesh that we have for the periodic hill, so basically the amount of collocation points is a trade-off. You don't need to resolve the gradients as much as you have in a RANS simulation. You have a coarser mesh, but still you need to be able to propagate the information of the residual from the domain to the boundaries, because the loss function needs to also match the boundaries. So you cannot get away with 3 points or something like that. You need to have a reasonable resolution, but you can have coarser than with other numerical methods.
Right. Okay. If you go if you go to slide 27, you apply the autoencoder to some sort of 3D channel flow problem.
The urban environment, the simplified urban environment.
Oh, simplified urban environment. So the size of the data would be not that
this one, right?
a high resolution.
So
how big of the simulation data is this?
So these are 1,200 instantaneous fields. This is a simulation that, if I remember correctly, is around 100 million grid points in the full domain. And we extract a 2D plane that is at the center of the obstacles, so cutting through the middle, and it's a spectral interpolated on a mesh of this size, so 96 times 192 grid points. So we really reduce the amount of data from the problem, although the multi-scale character of the complex turbulent flow is present in these snapshots that we consider.
Okay, so you treated the data to 2D and then trained the CNN.
Yes, we only consider a 2D plane. This could be done in 3D as well, of course, but as a first assessment, it's just the 2D.
So when you go from 2D to 3D, the scalability of the training of the neural net CNN should be considered. And any idea how you're going to do that?
Yeah, that's a very good point. And of course, we have run into some problems of the scalability of TensorFlow itself. No? So we had to fix some of the parallelization of the training in TensorFlow. So we are working on some larger cases, 2D much larger and 3D. And yeah, I mean, it seems that it's feasible, it works, but there is quite some work to be done on the computer science aspect of it. Yeah.
Sounds good. All right. Okay. All right. Another question by Juan. He asked, did you try different sampling strategies for the work of RANs with pins? And if so, did it make any difference in the results?
What do you mean with sampling?
I think he meant the collocation point selection.
If you mean the grid, yeah, the collocation. Exactly. So for the collocation, it's connected with a discussion that we were having before. So yeah, we had to play a bit with the distribution of the mesh. It's convenient to have, I mean, as you would have in any numerical method, finer resolution where there are larger gradients, but it's not a big requirement because of the automatic differentiation. The more important thing is that the points are quite uniformly distributed through the domain, so you can actually match effectively the boundaries. So that's the key. Because pins, the problem is that pins will always give you something, even if the boundary data is not consistent with the flow and things are a bit tricky. So you should, make sure that your mesh is at least fine enough to be able to propagate that information effectively. And the quality of the boundary conditions is going to define also the quality of your solution as well.
All right. Last question from me. I think you introduced the two different autoencoder for the reduced to the models. One was the hierarchical autoencoder, and the other one was CNN-based autoencoder. Yep. When you compare those two autoencoder, which one was better in terms of the compression?
So the CNN autoencoder was better. I can show now the results. The less things you impose, the better the compression. So I think the results are here, right? So the autoencoder, the CNN autoencoder, gets 94% of the signal with 5 modes, the hierarchical 91%, and the variational 87%. The hierarchical with 5 modes is worse than the CNN because you have that additional property of optimality. I mean, it's ranked.
Most structures in CNN, hierarchical one. But it's more interpretable for the hierarchical.
So the hierarchical is not more interpretable. But the modes are ranked in terms of their energetic contribution to the reconstruction. So if you want to truncate, if you want to have a reducer model and truncate, the hierarchical is better.
I see. Got it. Okay. Sounds good. All right. Okay. So I guess that's about it. Well, if there's no more questions, I mean, let's thank our speaker, Ricardo, for the wonderful talk he gave us.
Thank you very much for the invitation.
And as he said, if you guys want to directly contact the Ricardo, please do so, and initiate the collaboration, future collaboration. That's all about this seminar, the motivation of this seminar. So, well, thank you so much for the good talk, and keep in touch. And
thank you very much, and yeah, have a great day. Bye bye.
All right.